So in this talk, I hope I can convince you of something which a lot of us in the paleo community have long assumed, but we've been lazy. We've been very lazy about it, and Carl has been keeping me honest and trying to, really make me prove it. So here's what I'm going to try to do today: is to actually convince you that the DO events, these so-called abrupt changes that we talked about, first is discovered in Greenland, really do occur in some form or other, but we're not sure what, at low latitudes. So I've started calling them semi-global because the sort of half of the Earth seems to be involved. And I want to emphasize that we don't really know if that's temperature. All we really know is that Greenland and Europe have very big, fast, abrupt temperature changes. The changes that are seen in the low latitudes could be hydrological, could be rainfall and wind changes rather than temperature changes. So we really still have a long way to go on the data side of things in answering questions like, how much did the tropics change in temperature during the DO events? I think one of the points that Carl has really made me focus on is when we say that this DO event has been identified. What do we really mean by that? Does that mean that the wind changed direction, or did that mean that the temperature didn't change at all, but the rainfall went from being in the summer to being in the winter? Lots of things can change paleoclimate proxies without necessarily causing any pain and suffering to ecosystems or humans. So I think we have to really start being more careful in the paleo community about what we mean when we say that an event has been identified in a proxy record. Okay, so I want to acknowledge a lot of people whose work appears in this talk. This is very much a collaborative exercise. Ice cores are what I'm going to start talking about, and I'm going to spend most of my time talking about them just because that's what I'm most familiar with. I don't mean to slight the other kinds of paleo archives, but I'm just not as well versed, and so I might as well talk about what I know about. I think there are some unique aspects to ice cores that do make them more useful for talking about very rapid abrupt climate change on the order of 10 years, let's say. If you want to define abrupt, I would say something that happens in 10 years rather than 1,000 years, and we're not interested in things that happen in nanoseconds or some days. So the 10 years is sort of that time scale that we're interested in here. And ice cores are very uniquely capable of answering questions about the 10-year time scale because they do preserve annual layers in many cases, especially the Greenland ice cores. 40,000 years ago, an annual snow layer in Greenland is still typically 2 centimeters thick. So you've got lots of material to work with, and the ability to count annual layers, so you get good dating. And you not only get good dating, but you can tell whether an event happened in 15 years or 3 years. You can tell the difference between that kind of thing by looking at the individual annual layers. This is a very famous record. You've all seen it before, probably, the Dansgaard-Oeschger events. And so time is always going to go forward from left to right in these graphs. I'm trying to change all my talks around to do that because I agree that it's too confusing to be switching back and forth between the sort of physics community who does it one way and the paleo community does it the other way. So let's all. I'm urging all of us to start doing it this way. The events in Greenland on this particular scale are all about 10 degrees C in amplitude, and I'll talk more later in the talk about how we think we know that. This parameter here, delta O18, has some substantial uncertainties associated with it, and so one of the things that our community has been doing is coming up with alternative indicators, one in particular based on isotopes of nitrogen and argon gas trapped in the bubbles in the ice, which give a totally independent method for checking this O18 thermometer, and it does give about 10 degrees. So we think we're on solid ground in Greenland, at least, in saying that these were big rapid temperature changes of 10 degrees or so. Of course, we know nothing about how much the mid-latitudes or the tropics change. That's just something that's valid for Greenland only. Okay, here's the big question that I alluded to in the introduction. How spatially extensive were these events? Could you make a null hypothesis that it was just Greenland? If you could, then there's a lot of interesting things, and I think Carl will talk about that some more. Some ideas about how you could explain these events if they were just around Greenland. Now, I hope to convince you in this talk that the data don't allow you to do that, that they really have to be more extensive than just Greenland. So I'm going to try to reject the null hypothesis in this talk, but let's look at the evidence. Here's a sort of a cartoon of places where people have proposed that they've found the DO events in red. And you can see it's mostly the northern hemisphere. Really not much at all in the southern hemisphere. There was sort of controversial findings in a few places. They've sort of evaporated as the data have gotten better. So it really does look like it's a semi-global phenomenon, mostly a northern hemisphere phenomenon. But there's a big problem here in that a lot of these records, although I really don't want to offend anyone who might be listening to this, a lot of these records aren't very well dated, and that's a real problem in trying to make a statement about the spatial footprint of these rapid climate change events. Because
Jeff, can you tell me what well dated would be? I hear that thrown around a lot.
Okay, so let's say that the DO event, the warm period, lasts for 1,000 years. Let's say that your sediment core is dated to plus or minus 5,000 years. So I mean, not very well dated in the sense that the error is much larger than the length of the event itself. So a well-dated event would be one in which the error was, say, 1/10 the length of the event. So say 100 years as opposed for a 1,000-year-long event. Then you have a little more confidence that synchronicity that you identify in two independently dated records is telling you that this is the same event and it really did have a wider spatial footprint. Okay, so let's look at a couple records in particular. It can't be comprehensive, obviously. There's just way too much data here, but I'll focus on what I think are some of the better dated records. The ice core in Greenland, the Carioca Basin records for the period from 9,000 to 15,000 years ago, which is a limited subset of that record, of course. It goes back much farther, but the dating gets lousy farther back. And then the stalagmite, there's what are they called? Stalagmite records that are uranium thorium dated, so they have really good radiometric dating from China. And there's a few more. There's one from Oman, and I apologize for people that I may have left out. There's actually quite a lot of stalagmite records coming into the literature right now. Okay, so I mentioned this problem that the dating's not so great. There's two exceptions, at least two exceptions that I want to focus on, these Carioca and then even if you have good dating, which I think in these cases you do, you have another problem in that you have a proxy for climate or something. Who knows what it is, but maybe it's temperature, maybe it's rainfall, maybe it's wind. But the interpretation of the proxy is often not straightforward. And I think in these cases, we still really don't know what the proxy actually means. We've got O18 in a stalagmite, in a cave deposit. What does that actually mean? It probably means O18 of the rainfall that falls, because the signals are way too big to be direct temperature signals. So it's something about the O18 of the rainfall. Well, if you look in the tropical regions, the O18 of rainfall doesn't vary with temperature, it varies with the amount of rainfall typically. So monsoon rains, when you extract a very large fraction of the water vapor from the atmospheric column, you get a much more depleted O18 signature. and if you only have a little bit of rain, you get a heavier one. So I mean, this is the so-called amount effect, and so it's been the authors of these studies attribute it to the monsoon strength. They're probably right, but I think that I just want to highlight that there's still a lot of that remains wanting in interpretation of the proxies. So here's this Carioca Basin Venezuela record, and I emphasize that these age scales are independent. They haven't been wiggle matched. So this is based on layer counting of an ice core. This is based on layer counting of a sediment core that happens to have resolvable annual layers because it's anoxic. It's from an anoxic basin, the Carioca Basin. And the time scale is anchored at 9,000 years by matching to the tree ring record, which is arguably one of the best records we have, at least, but it only goes back to about 11,000 years. So that's the so-called dendrochronological record. So this is I would argue, to 15,000 at least is a well-dated record. And you can see that the correspondence to Greenland temperature is certainly very suggestive. Even little details like this little event here, which actually has a name, it's called the Older Dryas, not to be confused with the Younger Dryas. The Older Dryas was just a short little event, something like a century long, but it shows up in Venezuela in the color of a sediment core in Venezuela. Well, this has been interpreted by the authors as a wind signal. When you have a lot of wind, you have a lot of upwelling, you have a lot of biological productivity. That makes more white-colored shells rain down on the seafloor, so your sediment core looks white. So white is down here. So wind is down.
Accident, isn't it? Because there's so much other wiggling about of all the other ones that just doesn't match. So how can you just say that one that happens to coincide? Oh, that fits.
That's a very valid point. I mean, it's a good question.
The one after that.
The one after that is
This, yeah, right. Okay, so we'll say this one is a mismatch. There's no.
You have to do a statistical test.
Yes.
It won't pan out statistically. See, the second blue one there has no statistics.
Right. This one. Well,
Yeah.
that one probably actually is that one.
Well, yeah, but
Obviously, the Younger Dryas is beautiful, isn't it?
There's more information. What I'm trying to say is that I'm not just looking at this in isolation. I mean, I'm looking at lots and lots of different records, and so it's not fair because I have a lot more information than I'm sharing with you. You're just looking at one picture, but
I always have this problem when I look at
yeah.
record. I always get into this
Right.
I will talk
mental
about
chaos.
this.
Right. What I'm doing is a Bayesian approach. I'm using prior information.
Well, but
Right.
we'd like to see the prior.
You mean you're
Yeah, you will. Okay. Let me just go on here. This. Sorry.
You're using expert information in your head. Very clever scientists.
That's right. That's right. Yeah. Okay. Well, it's a voluminous. You're right. I think it's a real problem. It has to do with the fact that it's a voluminous data set, and so people who are in the business like myself, we look at hundreds and hundreds of these records, and so it is a real problem in communicating to an audience. The full availability of data. But let me go on. I think you'll feel a little bit better when you see maybe 10 as opposed to just one. Okay. I hope you'll feel a little bit better when you see.
What would be that you have selected them? My experience is that you certainly can find with your hundreds of series many which would fit perfectly well, and many which would just do the box. Then you have some nice argument saying this data set doesn't fit because of. If you have really thought about it, you have your prior.
Yeah.
Because of the prior, you argue like that.
Yeah.
Not you personally.
Right.
So there's certainly.
No, that's a very important point, and I'm fully in agreement with the point you're making. But I'm going to show things here that records like gas records. Let me go on, and I think we'll have this discussion at the end of the talk.
There is a point related to Simon. It's helpful to see all the records. not just the ones.
Right. So you see the bad ones too.
Yeah, so that you can make a judgment as to whether
Right.
this is
All the random subset.
Yeah, there is a tendency to censorship.
Mhm.
You show the ones that agree with the hypothesis. You do not show the ones that don't. That's the underlying difficulty.
Well, I will show some that don't. So let's have this continue the discussion at the end of the. So anyway, this is another piece of evidence that that does support a link with areas outside of Greenland. Though again, what kind of a link is not entirely clear, but I would argue, just looking at this by eye, that the Antarctic 018 record has some relationship to the Greenland 018 record. Now, Carl has published a paper saying there's no relationship, but that was also a slightly different ice core. This is a new ice core. I think it's probably a better quality ice core because the other ice core was drilled in 1968, and this is drilled in 1999. So I think the data quality is also an issue here. So looking at this, I would argue that something is related here. You see abrupt coolings in Antarctica when you see abrupt warmings in Greenland, and so I just tried to do a very, very crude statistical test of that by subtracting a linear trend from both data sets, and the correlation is minus 0.35. So I mean, and here's the actual data that the correlation was done with. So you can see that this is the Antarctic cooling that I pointed to before. Here's the Greenland warming that goes along with it. Now, I want to emphasize that these records are well dated with respect to each other, even though their absolute dates may be off by a few thousand years, because they're synchronized using atmospheric methane. This is the Blunier and Brook approach of using very rapid variations in atmospheric methane, and it's well suited to this particular type of claim because the methane jump happens to be right at this point. So you get one place in your ice core every 1,500 years or whatever where you are pretty confident that you've dated them relative to each other to within an error of plus or minus something like 200 years.
Does it also work with CO2 synchronization?
No, but you can't get good CO2 numbers out of Greenland ice. There's too much dust in the ice. Okay, so this to me indicates that there's some kind of relationship between Antarctic 018 and Greenland 018. What that means in terms of temperature, I think we still have a long way to go. But this is the kind of data set that's stimulated the bipolar seesaw hypothesis that you heard people mentioning before, that when you remove heat from the South Atlantic, the southern hemisphere cools, the northern hemisphere warms as a result. If you stop that process, you get an anomaly that looks like this, where the northern hemisphere is cooler and the southern hemisphere is warmer. And that kind of heat removal is supported by modern observations that show that the South Atlantic is unique in today's ocean basins in that net heat transport is northward, is not poleward. In all the other ocean basins, net heat transport is poleward. So this bipolar seesaw hypothesis, if you will, has been around for a long time, but I just wanted to point out that it really came from those ice core records originally. Here's this problem, though. As I said before, we really don't know that those small things in Antarctica are temperature. In Greenland, we've shown with nitrogen and argon data that they really are temperature. In Antarctica, we have yet to do that. So that's an important caveat. I mean, it is possible.
Can you explain that, how that was done in Greenland?
That's the second half of the talk, yeah. Mm-hmm. So, when you should be cautious when you look at Antarctic Delta 018 records, and we don't really know that they're temperature. They probably are, again, because of expert information. But there's a tremendous amount of effort in modeling that Jean Giselle has done and other people have to try to tell whether or not Antarctic 018 really is temperature. And the answer, the one sentence summary of all that work is yes, it probably is temperature. Okay, so here's the main meat of my talk today. I'm going to talk about gases, because I think gases have a special role to play in this discussion. The atmosphere is well mixed on a timescale of 1 year. That means if you measure the gas content of the atmosphere anywhere on Earth, it should be the same, with respect to gases at least that have lifetimes of much more than 1 year. So in other words, CO2 measured anywhere on Earth is essentially the same, leaving aside some very minor differences between the hemispheres. And so if it goes up because of some event, let's say humans burning fossil fuel or something like that, then you'll register it in ice cores in the north and ice cores in the south. Okay, and also if you have some production of CO2, let's say by factories, the atmosphere is going to sample the entire planet's surface in a sense. In other words, it integrates all sources all across the globe, and that's can be very helpful in asking questions about spatial extent of events, because I think I can convince you that the sources of certain gases in Greenland are likely to be next to zero. So that's one way to demonstrate that these events have footprints that are larger than just Greenland alone, and it's because of the fact that the atmosphere acts as an integrator of all different sources of spatial information, if you will, in a qualitative sense. So methane has an 8-year lifetime. That makes it respond rapidly to changes in sources. So in other words, if you suddenly doubled the sources of methane, you would approximately get a doubling of the concentration in methane after you'd gone out say 5 e-folding times or something like that. Anyway, you get an e-folding time of 8 years for changes in methane sources in terms of the response that you see in the atmosphere. So that's pretty fast, and so that's what allows us to use methane as an ice core synchronization tool, and it also allows us to say something about how the methane sources changed from ice core data on methane concentration with an error or a timescale error that's quite small. It's order of a decade. N2O is another gas, nitrous oxide, laughing gas, it's been called. So this has a longer lifetime, 120 years, but it still can give us information about changes. Atmospheric O2, molecular oxygen, that's what we breathe, has about 1,000-year lifetime, and also shows some changes in that. CO2 has a lifetime of something like 5 years with respect to exchange with other reservoirs, so it can change very quickly if sources to the atmosphere change. So here's how we get the gas information from the past, from bubbles in the ice. This is a photomicrograph of ice, and these are the bubbles here. And under cross-polarized light, you get the pretty colors. This is an ice crystal. So about 10% of the volume of glacial ice is actually air. There's a lot of air trapped in ice, and that's what we exploit to get these past atmospheric gas records. So here's the same picture you saw before with the Carioca Basin, but now I've added the atmospheric methane record that comes from the Greenland ice core. And so maybe this addresses your point. Is it Hans? Yeah, that this is not a situation where you can do any data selection, because the atmospheric gas record is the same everywhere. You measured it in Antarctica, you measured it in Greenland, you get essentially the same record, and it's been measured in 5 different ice cores in Greenland, and you always get the same answer. So it's a sort of a singular observation, if you will, and it varies very closely with Greenland temperature for reasons that are not completely understood yet. But perhaps more importantly, on an independent time scale here, the methane in this Carioca sediment core, color vary quite closely together. And so this is the kind of information that, in my view, actually makes me think, gosh, there must have been something happening outside of Greenland. Because to change the atmosphere, you've got to have a really big change in sources. The annual budget estimated for this time period is 100 teragrams. That's 10 to the 12th grams of methane. And for this time period, it's 160 teragrams. So you've got to have an increase in 60 teragrams of methane being produced somewhere. That's a lot of methane. And so you can't do that with Greenland, as I'll argue in a moment. Here's another record compared with the atmospheric methane. This is a record from the same core in the Carioca Basin, but now it's a different proxy. It's the magnesium-calcium ratio, which is alleged to represent sea surface temperature, which is plotted over here. And you can see there are big changes in this ratio. So changes on the order of 5 degrees C in sea surface temperature that are coherent with the atmospheric methane record. So that, I want to emphasize this may not represent Venezuelan air temperature. It's possible that the strong upwelling that you get in this basin cools the surface water. We know that whenever you have strong upwelling, you can get cold sea surface temperature. So this might be just another record of upwelling, just like that color scale I showed before. But at least it does show, a temperature record that's thought to be reliable from a well-dated, low-latitude core that has a pattern that looks a lot like an atmospheric trace gas. To me, that's probably the strongest argument in this vast field of weak arguments that the DO events really did occur outside of Greenland. So here's the argument about why I think you can't do it with Greenland alone. This is a model study of present wetland emissions. That's where methane mostly comes from, by the way. I failed to mention that. Prior to human perturbation, most atmospheric methane came from swamps, from wetlands. And you can see there's nothing in Greenland, essentially. And at the last glacial maximum, there's, again, nothing in Greenland. It's covered by ice. Well, it's covered by ice today, but there's a lot more ice, and so it's harder to get any kind of methane source in the surrounding regions from Greenland. So you really have to get it from the mid-latitudes or the low latitudes. I think there's really no way around that.
What about the oceans?
Oceans are a sink for methane. They actually take up methane because of
Pieces, right?
well, this whole hydrate thing is something we're studying, actually. It's a very interesting question. I think that, the jury's still out on that, but it's going to have to be a very small term. I talked about 60 teragrams per year. Some people who publish studies about hydrate release say 4 teragrams came out from this single slide that happened once in the 10,000 year period. It's not a big flux, so. Okay. All right, so this is too involved to go into, but you can use slight differences between Greenland methane concentrations and Antarctic methane concentrations to infer the past atmospheric difference between the hemispheres. Today, there is actually a difference in the atmospheric concentration due to the fact that most of the methane sources are in the northern hemisphere. The magnitude of that difference tells you something about the distribution of sources with latitude in a very crude sense. You can make a very crude 3-box model with an equatorial box, a north box, and a south box, and you can invert this data for the past. And what you find, to summarize briefly, is that you can't do it without the tropics. You have to, especially this bowling Alarod warming, which is also known as Dansgaard-Oeschger number 1. That you've got a big increase implied by the lack of change in the atmospheric gradient, actually. And so that again suggests low latitude is very important for causing these big atmospheric changes. Therefore, something had to happen in the low latitudes. Not necessarily temperature, could be rainfall, could be either temperature or rainfall. Its methane production is known to very strongly with temperature. So, and here's the N2O. This is a very interesting new data set from Jacqueline Flukiger, who's at Boulder right now. She's analyzed the nitrous oxide content of ice cores and found that they have a signal that looks very much like the Greenland temperature record. Now, I want to emphasize there's no timescale uncertainty here because these are coming from the same ice core. You're looking at the gases in the ice core and the ice in the ice core. So it's very clear that atmospheric concentrations of this particular biologically produced gas varied in concert with Greenland temperature and with methane. So it looks, to first order, and the N2O record looks a lot like methane. Those blanks are because it hasn't been run yet. They're still working on that. So the sources are thought to be about half tropical soils and about half oceanic subtropical oxygen minimum zones where you have denitrification going on. So you can't do it again with the high latitudes. You've got to have either the mid latitudes or the tropics to get the N2O variations. So the sinks are probably constant in time because they're mostly in the stratosphere. So this is the N2O record again, blown up for these two big events here, and this is the same data you saw before. The methane variations are fast. This is very typical. You always see fast methane variations in the ice core record that seem to just follow on the heels of the delta 18 and the temperature change, probably within 30 years or less. And the N2O seems to perhaps start up a little earlier here at this particular event, which may be a really interesting clue that something in the system, perhaps in the subtropics, perhaps in the tropics, changed before Greenland changed, and that may give us some kind of a clue about mechanisms of these DO events. I'll skip that, running out of time here. This is I said I would mention the atmospheric O2. This is a change in the isotopic composition of atmospheric O2 that occurs on these millennial timescales. This is Heinrich event 4, and you can see there's about a 0.2 per mil change compared to a 1 per mil change for the glacial to interglacial change. So the atmosphere is in oxygen, which is very abundant gas, is seeing some big change associated with these climate variations. And I want to emphasize that O2 is made both in the ocean and on the land. So you can't just appeal, like with methane, maybe you could appeal to some local region in West Africa or something that was making methane, and you could somehow minimize the spatial footprint by saying it's coming from one small region. Well, photosynthesis is all over the Earth. This kind of doesn't allow you to just minimize the footprint to a small area. Sorry? That's a very fascinating topic, which we don't fully understand, but it's probably due to aridity in Antarctica. We think that these are times when it stopped snowing, and so the firn became extremely porous, and you had deep air convection in the snow layer. And it may be ultimately another way of using gases to learn about local climate conditions. This does not change in the atmosphere. I failed to mention that N15 is constant all the time in the atmosphere, so it's telling you something about local climate. Okay, so CO2 also has some abrupt changes. It's not very big compared to the whole glacial interglacial change of about 80 parts per million, but it's about a 10 part per million little step right here. And so CO2, again, is not something that's made in a special region. CO2 is exchanging with the entirety of the terrestrial biomass and with the ocean surface. So while the exact cause of it remains unknown, I think we can conclude that Greenland alone could not have done this. Okay, the ice matrix too has indicators of far field climate. You have lots of dust in the ice cores during glacial time, and it's been isotopically fingerprinted as being from certain regions, like Central Asia for Greenland. And so it's not time to go into all the arguments here, but the bottom line is that you've got to have had hydrological changes in the source region. This is what the dust looks like in the ice. this very dark ice. Here is the glacial ice, and this is the Holocene ice, the clean ice. It's a huge difference in dust content, often 2 orders of magnitude.
So there's that picture we've been down.
This is from a helicopter. Yeah, we're looking south along the margin of the Greenland ice sheet. That's our tent right there. And this is a place where old ice comes up to the surface by ice flow. So you can get as much ice in old air as you want with a chainsaw instead of an ice core. So we melt down 2 tons of ice per sample to get radiocarbon of methane to assess this clathrate hypothesis, which is, you could do that because the clathrates have no radiocarbon there, as opposed to the wetlands. The wetlands are the modern component of radiocarbon. We still don't have the answer on that, but that's ongoing. Okay, so I'm running out of time. The summary of all this evidence: methane suggests abrupt hydrological change in the lower mid-latitudes. The calcium suggests that in central China anyway, you've got to have had abrupt hydrological change. By abrupt, the dust often changes in 3 years. It's really fast. So, I mean, it's faster than we can resolve with the nitrogen and argon technique, which has a limitation of about 20 years. So, we think that we can say that the trade winds probably weaken with the abrupt Greenland warming. That's the Carioca, and that's been attributed to migration of the ITCZ, supported by lots of other kinds of evidence from that same core, like the iron content, which shows heavy rainfall at the same time that the trade winds stop. So it's consistent with the idea that you had the ITCZ migrating over the site. And then there's all these biogenic gases that essentially are things you can't get changes from in Greenland. So they have to have been a lot of the low latitudes anyway. So that's why I'm calling these things semi-global. And I'm kind of out of time, but the next part of the talk was this, this is all published though, so maybe you could, come up to me afterwards, we can talk about that. Okay, thank you.